Okay, let's see. Everybody's there, right? I'm late because I clicked on the wrong link. I joined the wrong meeting. I'm not even sure what meeting I was in. But I joined a meeting and it was the wrong one and I got mixed up. And I don't know how I managed to get into the wrong meeting. Okay, so that's why I'm late. All right. Let's see. Everything's set up. You can see the desktop, right? Okay. All right. So we've been going back and forth between looking at how to implement closures and looking at how we can use closures. So today we're going to look at some more code of how we can use closures, and then we'll go back and look one more time at the details of implementing, because the details of implementing are a little bit tricky, but it also helps to understand how people would use closures, to understand it helps motivate at least how you would implement them. Okay, so I've got two folders of two examples that are two examples of uses of closures, and there's actually a third one I didn't have time to put up there. We'll maybe today or Wednesday we'll look at it, which is mimicking object-oriented programming. You can use closures to mimic object-oriented programming, but today we'll look at currying and sorting. Okay, so here's some code. Before let me explain currying first. So okay, here's currying is a technique that's used sometimes with functions. It's something you can do in any language, but if the language doesn't do it for you, it's almost useless. So we're going to introduce the idea of currying, and our language doesn't do currying, and Scheme doesn't do currying. The most famous language that does currying is Haskell, and also I believe, I can't remember if Rust does it too. I can't remember if Rust does currying automatically. Here's an idea. Here's a function of 3 variables. Here's using math notation. Okay, so there's a function of 3 variables. Okay, if I give you, like, what should you think of something like this? Suppose somebody says f of 3 comma x comma y. Okay, yeah, what is that? What can that mean? Okay, in a sense, that's a new function of 2 variables. Oh, see, I should make this y and z, otherwise it gets confusing. This is really a function of 2 variables. Okay. If you plug in one value if you give a function one of its values, in a sense, you've created a function now of 2 variables. Okay. Okay. Now you can do this. You can do this another way. You can say h of z is, say, f of. I can give some other values like 5, 8, z. Okay, so if I give the x and y values and I leave z undefined, then I can think of that as a new function of, yeah, okay. So what people thought about this, and they thought, here's what should happen, okay? Let me switch notation a little bit, okay? Define a function just like this. Okay, notice that I'm not going to use parentheses or commas. This is Haskell notation. So the function f of x, y, and z is 5 times x plus 4 times y plus 3 times z. Okay. Now notice over here I said, well, what if you took f and you only gave it one parameter and then give it the other two parameters? Well, you're really defining a new function, g of y and z, okay? Here's how in Haskell you would write that. You'd write f of 3. That's saying give f the parameter 3. And then what f gives you back is essentially this g function. F will give you back the function of, it'll do this automatically. It'll essentially automatically create that function there. And then if you want to, you could say g equals this. So now g is a function of two variables that you get by plugging one variable into f. This is called currying, okay? A function like this in Haskell has the ability to curry itself in the sense that if you give it only one of its parameters, it gives you back a function of the other two parameters, okay? Okay, so in Haskell, okay, now let's see how we could kind of do something like this in our language, okay? You can actually almost do something like this in Java, okay? I'm going to use a different, I'm going to switch to another, okay, so this was math notation. Then I switched to Haskell notation, okay? And now for a kind of, well, I'll use a Lambda notation. Okay, so here's a Lambda notation. Okay, f. So I have a function lambda x, y, z, and that function is the sum of the product of 5 with x, product of 4 with y, and the product of 3 with z. Notice this scheme, but so this is, I actually should say this is more of a scheme notation. Okay, there's the function, okay, there's the body of the function. Then I can define f to be that function. Okay. Okay, so there's f, there's the function f defined scheme ways. I can make this function a curried function. I could make it act like this Haskell function. Here's how I would define it. The definition is going to be a little bit weird. I define f to be a lambda that takes in an x and it returns, well, like here, when you gave f 3, it's supposed to give you back a function of two variables. So f is going to be a function, and when you give it x, it's going to give me back a function, a lambda, that takes in two variables, okay? Well, it's going to give me a function that takes in one variable, okay? Because now over here, let's go back to the scheme notation. Suppose I give something f of 5 and 8. Well, that's my function h, and it's a function of one variable. So if I give f a 5, it gives me back a function of two variables. But then I give that function at 8, I get back a function of one variable. So I'm defining f to be a function that takes one variable, and it gives me back a function that takes one variable. And that gives me back a function that takes one variable, okay? But what does that function do? That function is the function now that takes the sum of the product of 5 with x. There's the body of our function. The product of 4 with y and the product of 3 with z. Okay? Okay, now I have to close everything. Okay, now I'm closing the plus. Now I'm closing the last lambda, the middle lambda, the first lambda, and the define. Okay. Okay, now I've got a real strange kind of function. Okay. Okay. What do I get if I take f of 3? Well, if I give f3, it gives me back a function. So I get back my g. Okay. So that's essentially my g. G, I can say define g to be f of 3. G is f with, G is this guy here now. Okay. This G here is that one there. Okay.
Question about the
Yeah.
limitations here.
Pardon me? Wait,
So,
let me turn off this. My speaker's real low. Let me turn it up. Okay, go ahead.
I got a question about the limitations here. So if our first lambda expression was xy instead of just x, would you be still allowed to do this here?
What do you mean the first? Okay, which you talk about this one?
The outer one, yes.
Well, you can curry in clumps if you wanted to. Yeah, usually currying is done one step at a time. So over here, I'm like, here how I gave this guy one variable here. Okay.
Mm-hmm.
So that gave me a function of 2 variables. And here, now, what I'm doing here can be thought of 2 ways. Are you really giving me 2 variables at once, or are you giving me 1 variable first, which gives me back a function that takes in this variable and then gives me back a function? Or I could or I could lump these 2 together, and I could define it so that if you give f 2, that would be the x and y here, then it would give you back the function of z. So I can
So the
lump
unit of currying is
whatever
the
you want.
variables,
Yes.
not the lambda expressions.
Well, both. You know, the lambda expression's wrapped in with the variable. So this is a lambda of 1 variable. Okay, like here I could do it this way. This normally when you talk about curry function, you curry 1 variable at a time. But let me define f in kind of an odd way. So I'll call this FO for f odd. Okay, it's going to be curried in an odd way. It's going to take lambda x, y, and it's going to return the curried function, which is a lambda that takes in z. And then with that z, it takes the sum, okay, of the product of 5 with x, 4 with y, 3 with z. Okay, now close the product of 3 with z. Okay, close the sum, close the one lambda, close the other. Okay, now this one's curried, but in kind of an odd way. You know, I can say define h of f of 5, 8. I'm currying 2 variables at once. As opposed to this guy, like if I go here and I say, now like suppose I want to define h here. How would I do it? Okay. F of 5 gives me back a function that takes a variable, which would be the 8. And then I get, see the difference in notation? This is, you give the 5 to f, which gives you back a function that takes the x, which gives you back a function, which is h. Here, I defined f to be curried with 2 variables at once. So you give f 2 variables, and it gives you back the h.
So the way that you end up currying functions is still tied to how they're defined.
Yeah. Well, you will almost never see somebody do this. Nobody's going to curry a function in lumps of 2 variables at a time. Okay, so they're always curried like this, one variable at a time. But you could suppose I do something really weird. Suppose I have a function f of suppose I have a function k of x, y, z, w, u, v, and I want to curry it. Well, I could curry it in bizarre ways. I could have a function of 2 variables that returns a function of 3 variables. And then that function of 3 variables could take 3 variables and return a function of 1 variable. I could lump these 2 as one currying step and lump these 3 as another currying step. But that would be really dumb. You can do it. I mean, you'd be writing the code as a mixture of this kind of code and this kind of code. This one takes a function of 3 variables and curries 2 variables at once. Okay, it takes 2 variables and returns a function of 1 variable. That's not how any real programming language does it. They do it this way. They curry 1 variable at a time. Now, the trouble with currying in languages like Scheme is you have this really off, like, for example, how do I apply f to 3 variables? So here is f of 4, 5, 6. That's how you would write f of 4, 5, 6, right? Here now, here you'd write f of 4, 5, 6. So the function is defined to take 3 parameters. There you get 3 parameters. Okay, how do I call this function with inputs 4, 5, and 6? Very carefully. Okay, f takes in what variable? 1 variable, 4. Now, f takes in 1 variable. But what does it give me back? A function of 1 variable, but I have to call the function f gave me back on that 1 variable. Okay, now this inner thing gave me back a function of z. So there's 6. Okay, there's the mess you have to write to call f on 4, 5, and 6. Okay.
Is it not possible just to write it out as f of 4, 5, and 6?
No, not without language support. That's what Haskell does for you. Haskell lets you write this because Haskell's got this built in. Okay. See, now in Scheme, here's 2 definitions of f. Here's the uncurried definition of f, and here's the curried definition of f. I can, actually, let me call it fc. So here's f, and here's fc, the curried version. Here I called the curried version. If I call f, it's just f of 4, 5, 6. Okay. So I call f the normal way, but I call the curried version in this very complicated way. Haskell doesn't have a distinction between the uncurried and the curried version of a function. All functions are curried by default. So that actually writes out internally to Haskell, that is actually written this way.
Oh, so it's syntactic sugar.
Yes, for that. Yeah, in Haskell's functions are syntactic sugar for these curried function definitions. Okay, so Haskell does that automatically for you. So then you could call f, you can do f of 3 and automatically get back this g. Okay, so now in our case, here's how we define g. Oh, and then I should say that this is the curried f, and this is the curried f. Okay, so in our language, in a language like Scheme, you have to do the currying yourself. You don't get the currying for free like in Haskell. Now, what does this got to do with closures? Okay, so this is what currying looks like. Okay, here's what it looks like in math notation, Haskell notation, and Scheme notation. Okay, Haskell does it the most elegantly. Let's see, in math notation, math notation actually doesn't do it too bad. You can just, the way math notation is designed, you can just say 3 there. F of 3yz gives you a function of yz. And f of 5, 8z gives you back a function of z. Okay? So math notation kind of gives you currying if you want for free. Okay? Oh, I have an extra paren there. Okay. Okay. Scheme notation. Okay, there's the usual way to define a function. There's the curried version of the function. Okay. The curried version is a complicated beast to call because you have to do all these parentheses. You give the curried version one variable at a time, one parameter at a time, and it gives you back a function you have to call. So it keeps giving you back functions, so you have to keep calling them. Okay. So now it doesn't look so bad here, and it doesn't look so bad here. Well, look, it's starting to look bad here because it's got a lot of these nested parentheses. Okay. In Haskell, it's real elegant. Okay. Now, in here are closures. Okay. Because here's what we would need to start with this last lambda expression. Okay. So the last lambda expression, let's see, goes up to, well, no, this one's the defined, that one is the outer lambda. That lambda has two unbound variables. See, that lambda is a function of z. So that means x and y are unbound. Okay, so x, y are free in this lambda. Okay, so you have x and y are free in that lambda. So if you have a free variable, somebody's got to close it. The closing is this closure here. That environment, that this is the scope that closes that lambda. Okay, now if you look at this lambda, okay, in this lambda, x is free in this lambda. Okay, notice that in this lambda, x and y are free. In this lambda, only x is free. Okay, because the y is bound here. When you get down here, the y is bound there, the z is bound there, and the x is free. So in this lambda, there's a free. Okay, so this lambda needs a closure, and this lambda needs a closure. Okay, so another way to put it is that when you call the curried function here, it's returning a closure. It's returning a closure pointing, so this lambda returns a closure pointing to that lambda with an environment holding that x. Okay, and this, so that's what you get when you call f of c. When you call f with that parameter only, you get back an IP-EP pair that points to that lambda with the environment holding that x. If you call f this way with twice, you're getting this lambda. You call f with x and y. You're getting a pointer to that lambda with the closure to this guy. But this guy is well, you're calling that lambda with a pointer to this lambda, and that lambda is a closure that includes this. So you get a chain of closures. What you end up getting, it's tricky to write it out, but when you get to this one here, when you've applied the x and the y but not yet the z, you actually have a chain of two closures. You have this guy is being pointing to this guy, which closes the y, and this guy points to this guy, which closes the x. So you get these complicated closure chains. Now, the Haskell programmers almost never have to think about that. They get used to programming with curried functions, and you can do all kinds of elegant things when you program with curried functions. It's hard to show you because in Scheme, you don't have any elegance. In Scheme, programming with curried functions is a nuisance. Okay, but in Haskell, where the language supports it for you, there's all kinds of very clever little programming techniques. It becomes a style of programming. It's actually got a name. The style of programming with using, this is called a partial application. I've only applied part of f. And this is another example of a partial application. I've only applied, see, they call it partial application because we think of f as being applied to 3. That's what a function call is. A function call is a function application. It's a very clever little programming technique. You know, you can write very elegant code using partial application. It isn't something you can't do in other languages. You can do it in Scheme, but in Scheme you have to write very complicated notation. So you can use the style of partial application in Scheme, but no one's going to like it because the notation becomes unreadable. Haskell is designed to make partial application easy to use. Okay. Now we can turn this into real code. Here's a racket file. Actually, I want to show you something else. Before this is more. Let's let me just close that. How do you close a racket file? Oh, close window. Can't racket just close the current file and let you open another one? Close tab. I guess I didn't. Okay. Okay.
Oh.
Yeah. Let's try these. Let's put these into racket. Now I have to clean up. Oh, and I want. Here's an odd currying. So, okay. See if I make sure I did these right. Okay, let's see if these compile. Okay. I probably a mismatched parentheses. Okay. Let's see. Need another parentheses there. Oh, no. Oh, I can't define H 2 times. So this is H. This is the odd version of H. So make this one H odd because it was defined using the odd curried one. And oh, notice that. Oh, I'm glad this happened. Scheme has a very lousy tokenizer. Scheme doesn't tokenize very well. Okay, notice that that's the multiplication of 5 with x. Most languages would let you do that. Scheme treats that as one token. Scheme won't tokenize that properly.
So if you group any tokens other than parentheses, it'll just flip out?
It's certain ones. Yeah, it has a weird tokenizing rule. It's not as liberal about, it's not as knowledgeable about tokenizing as, I think the reason is you can define your own operators. So I think that what it is saying that that's your 5th multiply operator. See,
no,
I think it's not really that the tokenizer is bad, is that the language lets you define your own operators. So you could think of that as your 5th version of the star operator. Okay.
Lua lets you define your own operators too, and it doesn't do that. But
yeah,
then
but
again, Lua
it has to do with the way you
break everything. So.
Yeah, it may have to do with the way you name the operators. Like if that's a valid name for an operator, then it has to not. Okay, so I need a space there, and I need a space there. Okay, right. So now I can do things like, so notice that this worked. Okay, FC. Notice that FC is a procedure. it's, well, okay. What happens if you give FC 3? You get back a procedure. What if you give FC of 3, 4? Oops. You get back another procedure. Okay, you have to give it, yeah. So it's the curried F. So you give it 3, and it's giving you back the procedure of 2 variables. You give it 2 variables, it's giving you back the procedure of 1 variable. So to get a value, I have to give it one more. I have to call the last function it gave me and give it a value. See, so I gave 3 to the curried function, and it gave me back a function of 2 variables. I gave 4 to the function of 2 variables, it gave me back a function of 1 variable. I gave 5 to the function of 1 variable, and it gave me back 46. Okay, that's the same thing as f of 3, 4, 5. Okay, yeah. Nobody's going to really work with curried functions in Scheme. It's nice to know what curried functions are. They're an interesting application of the notion of closures, of returning closures. And they're very elegant if your language supports them for you. If your language doesn't support them, then you probably do not want to be using them. Okay. What happened? There. Okay. Okay. So this was an example of one particular function. I started with a function of 3 parameters, and then I wrote it in its curried form. And I also wrote it in its, then I wrote it in the odd curried form. You know, if you go down here, you can play with the odd curried form. Okay, the function curried in the odd way takes 2 parameters.
That's the wrong O.
Oh, that's the wrong O. Yep. Mm-hmm. Okay, notice it gave me back a procedure, but this is this one was curried in by, it lumped 2 variables together. Notice that I can't do this one. I can't do the odd one with 1 parameter. If I do this, I get back that I didn't give it enough parameters. Okay, see, this was wrong. See, I curried it, I lumped the first 2 variables together. I curried it in a weird way of lump the first 2 and then, yeah. Okay, and so this one, if I want to call it with 3 variables, I call it with 2 variables. That gives me back a function, and I give it the 3rd variable. Okay, there's my function of 3 variables curried in an odd way. And then if I want, I can curry it again in another odd way. This time I'll lump it the other way. Okay, and I'll call this curry odd odd. That's not a good name for a function, is it? Okay. Okay, so this is now curried in a doubly odd way. Okay, it's curried in a doubly odd way. The function takes in 1 parameter and just gives me back a function of 2 parameters. Okay, so it's a 1 step of currying. This one took in 2 parameters and gave me a function back of 1 parameter. This one takes in 1 parameter and gives me a function back of 2 parameters. Okay, and see, did I call it correctly here? I would now give it 1 parameter here. Yeah, Now I give it one parameter there, and I get back a function of two parameters. So what did I miss? Now I've got parentheses misbalanced somewhere. Wasn't this correct before? Okay. I don't know what I did wrong there. Okay. So now if I go down, I have these two oddly curried functions. One of them takes in two parameters and gives me back a function that takes the third parameter. What did I do wrong? See, I've got it all messed up now. That's the trouble with scheme. Scheme can be impossible sometimes to read. Somehow I got a stray parentheses in somewhere. Did anybody see what I did wrong? It was when I was. I got a stray parameter. I got a stray parentheses somewhere.
It all looks fine.
Yeah, and it was working a minute ago, and now these, like this one isn't working anymore. Save it, and then try to undo the changes here.
It looks like you added an extra parenthesis to it at one point.
Yeah, and oh, there's the mistake. There's the extra parentheses right there.
Oh.
Yeah, see, 4 of y. There, that guy there, and that guy there. Those were the wrong ones. Let's see if now I put this back over here. Okay, I think,
It runs.
Yeah, but let's see if the functions are defined properly now. Okay, so I've got the function that's oddly curried that takes in two parameters and gives me back a function that takes the third parameter. Okay, and then I have the other oddly curried function. So I have the other function that's oddly curried that takes in only one parameter and gives me back a function that takes two parameters. Okay, so I curried the function of three variables three ways. And then here's the regular way of currying it. The regular way of currying it is that you would give it the first parameter, and it gives you back a function that takes the second parameter. Then you call that function on the third parameter. Okay. So here's the function f curried three different ways. The normal way and two odd ways. Okay. You can curry any way you want, but the only way that really ends up making sense is to curry each variable individually. This one here is the right way to curry things, and then these are two odd ways to curry things. All right, so this is an example of currying of one particular function. Now, let me just show you what you can do with this. Don't need that anymore. You can define functions that do this for you. Now, this is a kind of challenging programming assignment in a way. In a course on functional programming, this is usually assigned as a homework assignment. The idea is define a function that curries another function for you. So define a function that curries functions. Okay, so this function here takes a function of two variables and curries it for you. Okay, so let me run this. Okay, so here's my function of two variables. I'll define a function. F2 is a function of two variables, and the function is just going to do the sum of x and y. So real simple. Okay. Well, what did I do wrong? Oh, I forgot the lambda. I mean, define F2 is a lambda of two variables that just takes the sum of the two variables. Okay, so F2 would take 4 and 5 and add them. Okay, now I have this function to curry it. Okay, the curried 2 takes a function, so I'll say define F2 curried to be the curried 2 of f. This function, we'll look at in a minute how it works, but this function here takes my f as its parameter and it returns a curried version of f. Okay, right? So how do I know it's a curried version of f? Well, f2 curried will take in one parameter and it'll give me back a function that takes the other parameter. So if I call it in its curried form, whoops.
The f function needs two parameters, and you just put 5 as one. Oh,
Let's see.
Maybe you can call f2c 4, 5, 6.
Well, no, the function like this one takes two parameters, and this
Yeah.
was the curried version. Unless I have something wrong. Let's see. The expected number of arguments is not mentioned. Expected 4 given 2.
Yeah, the number of parameters is wrong. Yeah.
Did anybody see my mistake? I called the wrong I wanted to curry. I curried f, which is a function I defined a long time ago. Yeah, I wanted to curry f2 here. Okay. I miscalled this here. That was supposed to be f2. I want to curry the two variable function f2 and call the new one f2 curried. Okay. All right. And then now should be okay. f2 curried of 4, then give it the parameter 5. See, gives me back 4 plus 5 is 9. Okay, so this function curried my function of two variables automatically. So it did for me automatically what we did over here when we took this function f and wrote out its curried definition. Okay, so this thing here more or less does that for you automatically. Now I have one function. This curries a function of two variables. This curries a function of three variables, and this curries a function of four variables. Okay, if you want to curry a function of 5 variables, you have to write another version. Okay, now how does it work? Well, first of all, it needs these helper functions. Okay, here's a function. Remember, if we go back over here, we started with saying that if you have a function of 3 variables and you give it one of its variables, you get back a function of 2 variables, right? So that's a form of currying also. So you have, that's the partial application actually. This step is the partial application step. So this is the partial application step. You give f just one of its parameters and it gives you back a function with that's waiting for the other 2 parameters. Okay. This function here takes a function and partially applies. I called it curry 2 to 1. Probably I should have called it partial apply. Okay, it takes the function f, which is a function of 2 variables. It takes one variable, plugs that variable into the f, and then returns a function waiting for the other variable. Okay, so curry 2 to 1 it should have actually been called partial apply 2 to 1. So it takes a function of 2 variables and applies one of the variables. Okay, so it should have been called, I call it curry 2 to 1, but it should have been partial apply 2 to 1. Then this curry 3 to 2 takes a function of 3 variables and one parameter, and it returns a function of 2 parameters. So it's a partial apply 3 to 2. This is a curry 4 to 3, takes a function of 4 variables and gives you back the partially apply. And it takes the function of 4 variables, a parameter, and it partially applies the function to the parameter. So it returns the function of 3 variables that you get by applying the parameter x to f, and then waiting for the other 3 variables. So that's doing this step here. Okay, so this thing actually it's this one right here, did this one right here. Took a function of 3 variables and a parameter, took a function of 3 variables and a parameter, and returned a function of 2 variables. That's curry 3 to 2 here. Takes a function of 3 variables and one parameter and gives us back a function of 2 variables. Okay, so then how do you curry a function? Suppose you want to curry a function of 2 variables. Well, let's see. Suppose you want to curry a function of 3 variables. Okay, you're going to return a function that takes in one parameter. And it's going to return the partially applied, it's going to return the curried version of the partially applied f on your one variable. Okay, so to curry a function of 3 variables, the function will return a lambda that takes one expression. Then it returns the curried function of 2 variables by partially applying f to one variable. Okay, this is typical functional programming. That's only 4 lines of code. How hard can it be to understand 4 lines of code? And the answer is, in this type of world, pretty hard. You know, there are companies that program this way. They're the minority of companies. It's a real open question whether you're better off programming in Java and C#, or if you're better off programming in languages like this. The rough rule of thumb is, if you have to write a program, you can write it in probably half the number of lines of code in a language like Scheme or Haskell. So if it's a 1,000-line program in Java, it'll probably be 500-line program in Haskell or Scheme. But you're packing more knowledge into those lines. They become kind of harder to read. But if you're an experienced programmer, which would you rather maintain, 500 lines of code or 1,000 lines of code? So
Depends on how they're written.
Well, assuming they're well written, you know, suppose you have
assuming both are well written, 500 lines of code.
Right.
Thank you.
So if you have your choice between 500 lines of well-written Scheme or 1,000 lines of well-written Java, but the trouble is the 500 line. I mean, it's a trade-off. The 500 lines of Scheme will be harder to read, but it's less code to maintain. You know, you do what you're doing here. You sit there and you stare at that code for 15 minutes, and then you understand it. So you can read the 500 lines of Scheme in about the same amount of time as you can read the 1,000 lines of Java. They take about the same amount of time to read, but there's probably going to be less bugs in the 500 lines of Scheme. Okay? And that's becoming a big debate in the world of programming now. Should people be expected to learn harder languages that need less lines of code but take a lot more thought per line of code, or should be people allowed to write in easier languages that need more lines of code and less thought per line of code? Another philosophy is that if you're spending more time per line of code thinking, you may have less bugs because you were forced to think harder about every line of code.
I have an extreme example of this. So for my distributed computing class, I was writing a network client, just sending text back and forth between two computers. In Java, I was able to write the program in the client side of the program in 30 lines of code. In Bash, I was able to write it in 1.
Well, that's probably not a fair comparison because Python does this trick. You're using high-level libraries.
Very, very high-level libraries, and they're all slow as molasses.
Yeah, that's a completely different analogy. Here, we're not using high-level libraries. We're writing pretty low-level code. We're using concepts like currying and partial application and closures and Lambda expressions. We're using ideas, you know, not libraries. In Haskell and Scheme, you need to write fewer lines of code using just these ideas. This has got nothing to do with pulling in libraries, okay? You know, each language will have plenty of libraries. You're not going to write the stack code every time you need a stack. You know, it doesn't matter what language you're using. You'd be a fool to write your own stack implementation every time you needed a stack. You're going to use the library. So when we compare languages like this, we assume that everyone's using libraries. So you know, you're not going to say, oh, I'm going to write it in Scheme and I'm going to implement my own stack. And when you write it in Java, you use the stack in the library. No, that'd be comparing apples and oranges. If you assume that you have similar libraries in both languages, which you tend to do, you tend to have the same libraries in all these languages. In languages like Scheme and Haskell, you still write fewer lines of code. Yeah. Yeah, when we do some more examples, I'll show you kind of like how that can happen. You tend to write about half, you tend to write 40% or like 60, 70%, 50, 60% of the number of lines of code. Okay, and this has been tested a bunch of times. You know, a programming problem has been given to experienced programmers in Java, C++, Haskell, and Scheme. And the functional programmers consistently come in with code that's like 60% of the lines of code, 50% of the lines of code. In terms of bugs, there's not that. If they're experienced programmers, the Java programmers probably won't have too many more bugs than the Scheme or the Haskell programmers. The amount of time it takes to write the code can be pretty similar. It's not like the Haskell programmers can write code in blazingly fast. It takes, it takes time to write code, but you do end up with fewer lines of code, and that's compelling. The fact that you end up with only 500 lines of code to maintain instead of 1,000 lines of code to maintain could be, that may in the long run turn out to be useful. But the biggest problem is that a lot of people can't wrap their mind around these higher level languages. A lot of programmers would just not be able to do this kind of program. If they were told to write web apps in Haskell, they'd go find another job. Okay. Yeah, unless you spend a lot of time training them. Sometimes you can spend a lot of time. Some companies have done it. They just say, okay, we'll teach you Haskell. You have to start back from square one and learn programming all over again, and you can learn Haskell and you can learn these kind of techniques. Okay, so there's an example of a sophisticated use of closures to build curried functions. In languages like Java and Scheme, it's just not that useful because the language doesn't do it automatically. So you're stuck doing it by hand. Let me show you. You can do this in JavaScript. This is a page that somebody wrote in JavaScript. Let me find the example. I think I've skipped it. There. Here's what it looks like in modern JavaScript. Okay, the function add is a function of two variables, and it just adds them. Okay, here's the curried version of add, and in JavaScript you can write it kind of elegantly. Add is, it's a arrow, so it's a lambda expression that takes in one variable and returns a something. Well, what it returns is a lambda expression that takes in something and returns that expression. Okay, so there's curried add, and it's, look how nice it is to write it. So the trouble is calling it's not so nice. Here's how you call add with two parameters. You have to use a bunch of extra parentheses because you're calling this function with one parameter, and it gives you back a function that takes the other parameter.
That's a lot better than what you have to do in Scheme.
Yes. Yeah, it's still, modern JavaScript is getting to be kind of, this is not bad. This is almost currying for free, almost. Notice that writing the curried function is for free. That's actually the way you would write it in Haskell. You would write it in Haskell almost exactly. This guy is a Haskell programmer. That's how you write things in Haskell. You write a comment giving the type of the function, then you write the function below it. So he's actually more or less showing you here that you can use almost literally Haskell notation to define the function, but then you have to call it in a slightly awkward way. Okay, so in modern JavaScript, you can do currying almost for free. And so this is kind of a neat article. He's using a very modern version of JavaScript. So he's using these arrow operators. If you wrote this in JavaScript a few years ago, it would look a little bit more like the Scheme one. You'd have to write it in a more verbose way. I don't know if he's got the more verbose way in this article. So he's choosing to use the fairly modern JavaScript notation here. Okay, so he's using the modern JavaScript notation, which lets him define the curried function almost for free, but then he does have to call the curried function in kind of an awkward way. Okay, so that's kind of neat. Curried functions are they're a tool to functional programmers. They're a nifty tool that can make some kinds of code more elegant and easier to read. Okay, now let's look at another example of using closures. Okay. here's the program that's going to sort things. Sorting is a really good example of what should be a generic operation. If I tell you to sort an array, well, okay, here's a list of countries. Each country has a name, a population, and no, I'm sorry. This is name. Oh, I forget what these word numbers even meant. I don't even remember what those numbers meant now. It was like name, area, and population. I think this was name, area, and population in millions. I think. You know,
Those look like they would be the right numbers.
Yeah, yeah. So I think that's name, area in square kilometers, and population in millions. Okay. So I got this data from some example somewhere. Okay. Okay. What would you do to sort this? Okay. It's a list of 3 tuples. Well, there's lots of ways you can sort it. You could sort it alphabetically by the name of the country. You could sort it numerically by the size of the country. You could sort it numerically by the population of the country. What if you sort it by alphabetically and you get a tie? You know, or what? No, that's not. You wouldn't have a tie. What if you had a tie in the country? What if you sorted it by country, but you ended up with a tie? What would you do with the ties? How would you sort the ties? Maybe you could sort the ties by population. So if you had 2 countries with the same size, you would fall into this thing. The question becomes, how can you write sorts in this generic way? You know, where you would change the parameters of the sort. You want to have one sort. You don't want to write sort by name, sort by population, sort by area. I mean, that's what you would do in the old days, and you would actually just have, suppose you have this data structure, and you sometimes need to sort by area, sometimes you need to sort by name, sometimes you need to sort by population. In the old days, people would literally write 3 functions: sort by area, sort by name, sort by population. But that's doing lots of code duplication. What you want is what in modern language we would call a generic sort or a parameterized sort, something that could sort in lots of ways. We write one code that could sort by lots of ways. Now, Java has this. For example, sorting arrays. Here's the function that sorts arrays. Okay, this is the function that will sort this array. Now, it's a generic function in 2 ways. It's doubly generic. Okay, it's generic in what Java calls the generic way. It's a generic array. So it could sort an array of ints, or it can sort an array of strings, or it could sort an array of doubles. Okay, now if you actually go up here, you can see the old-fashioned way of doing things. I mean, I don't know if some of you have seen this in some other classes I've taught. This is actually a super important idea. What we're talking about here is a phenomenally important idea. Let me get down to the sorts. Okay, how many sorts are there? Well, there's sort byte arrays, sort char arrays, sort double arrays, sort float arrays, sort int arrays, sort long arrays, sort short arrays, sort object arrays. Now, some intern got stuck with writing all that, because what are they going to do? Write 15 highly redundant pieces of code. And that's what people used to do before Java had what we call generics. You had to say, sort an array of char, sort an array of float, sort an array of int, sort an array of long. Then somebody came up with a way of saying, well, sort a generic array. Okay, that was one kind of generic. Okay, now there's another kind of generic here. Okay, when I sort that array, suppose it's an array of int, or suppose it's an array of string. How do I want to sort it? Do I want to sort it ascending or descending? You know, do I want to sort? I want to be able to say, here is the comparator to use in comparing elements of the array. So This thing is generic in two ways. He's generic in the type of the array, and he's generic in the way he compares elements. This thing takes a comparator. Okay. These different kinds of generics have names. One of them is called parametric polymorphism, and the other one is called let's see. Try to remember what one's called parametric polymorphism. Oh, I can't remember the name of the other one. This one, I believe, is the parametric polymorphism, and this one is another kind of polymorphism. Notice that we've got a sort function, and that sort function is undetermined in a couple ways. When the person wrote the code, it was not yet determined what it's an array of. So it's generic in what kind of an array it is. And it hasn't been determined how to compare two items from the array. If you give me two items in the array, how do I decide which one is the larger of the two? If I'm sorting ascending and you give me 2 and 3, 3 is the larger of them. But if I'm sorting descending and you give me 2 and 3, 2 is the larger of them, because I want it to come after 3 in a descending sort. Okay, so when I write the code for this sort, I'm leaving it open what it's an array of and how I'm going to actually compare two items. Okay, so that's the modern way of doing sorting with generics. Now you can even do this in C. Like look at, I don't know if you ever looked at the C sort function. The C sort function is actually quite generic. It takes an array of what? Notice that it could be an array of ints, or it could be an array of doubles, or it could be an array of strings, because it's an array of what?
Void.
Void. Yeah, it's essentially this older Java idea of an array of objects. It's not this kind of generic in Java, it's this kind of generic, where they said, oh, let's sort an array of objects. Okay, now but then you also give it a comparator function. There's a function pointer. This guy here is a function pointer. It's the thing that knows how to compare two items from the array. Okay, so now notice that this thing, a comparator takes in two pointers, but they're pointers to void. Okay, but it takes in two things from the array and tells you which one of them is larger. When you write code like this, you have to cast these pointers. Like suppose you know you're actually sorting an array of ints, then you have to cast all these pointers back to int. Okay. Now, the sort function, okay, the sort function, if you look at the code for this, the sort function doesn't know what the type of this is. It expects the comparator to know what it's comparing. So if the comparator really thinks it's sorting ints, this better be an array of int. If the comparator thinks it's sorting strings, this better be an array of strings. In the C language, nothing keeps that straight. You could give this an array of strings and give the comparator a comparator of ints, and your program just blows up. In Java, because of the way Java was designed in C++, what's going to happen is if you screw up the sorting, where'd it go? See this T? They have to match. If it's a comparator of ints, it's got to be an array of ints. If it's a comparator of strings, it's got to be an array of strings. You can't goof those up in Java. You can't have the sorting think it's sorting strings while the comparator thinks it's comparing ints. In C, because it's an older language and generics weren't designed very well, you could screw up a C program royally by calling sort on an array of strings, but pass it a comparator that compares integers. It probably won't crash. It'll just give you a very mucked up sort. Okay, so this is the idea of generics. It turns out that closures can be used to provide very powerful generic code. Closures are a way of doing generics. Now we run out of time, but we'll start with that here in this code here. We'll see that there's this code, you can download it and start reading it. This sort is generic. we'll see that it could sort any kind of an array more or less with any kind of comparator. Okay, and it's close to the C style, not the Java style, because you could muck this up too. You could have it sort an array of strings and give it a comparator of integers, and it won't know the difference because scheme is an untyped language. So in that case, it's as bad as C. But this code here, if you write it in Java, is going to be about 5 times more code. To do this in Java is about 5 times the amount of code it takes to do it in Scheme, because Scheme's use of closures makes this really elegant. Okay, so we'll quit there. We'll look at this code. This is very interesting code. If you're interested in modern programming languages, if you wonder why Rust is being designed the way it is, if you wonder why Java and C++ are moving in the direction they're moving, these examples have a lot to do with it. These examples capture what modern programming languages want to do compared to what they used to do with this kind of a mess of having 15 different sort functions. And Java has gotten rid of the 15 different sort functions. You only need this one sort function in Java, but that code is not very elegant. That code is, the Scheme code is way more elegant than the Java code would be. Okay, so we'll quit there. The code is up on the course website. The query code and the sort code is up there so you can look at it. And we'll finish talking about the sorting code, and then we'll also look at creating objects using closure. We'll do baby object-oriented programming using closures. Okay, so if you have questions, send me an email. If you have questions about the programming assignment or anything like that, when's it due? Is it due today or Wednesday? I forgot.
It's today.
It's due today? Okay, there'll probably be one more short homework assignment up there. There'll probably be one last short homework assignment for the semester. So look for that soon. I think there'll be one last I may just pass on the the exams, okay? Because you've had 5 programming assignments. They've been good programming assignments. So I'm thinking that we'll pass on the exams. The exams are hard to write for this class because there's so many ideas. I think the programming assignments capture the ideas much easier because you see the programming assignments are pretty substantial. So I think there'll be one more programming assignment. They'll talk about some of these involving closures, something to do with closures, and then that'll be the last thing for the semester, okay? And so if you've got questions about the current programming assignment, let me know. And all right, and I will end a meeting. All right, bye.
Bye.